Hello everyone, hearty welcome to my channel. In this lecture, I am going to explain you about one of the source coding algorithm, Shannon Fano coding with an example. Before going to that example, let me discuss with a few points about source coding algorithm. Generally, source coding algorithms are very important role in the digital communication system where that input discrete symbols are going to convert in terms of binary code words. We know very well that digital communication system is going to process only the information if it is in discrete format, and the mode of transmission is completely in terms of digital symbols, which are symbol 1 and symbol 0. Whatever the information is there in the input side, that will be converted into the stream of binary output 1 and 0. So in that process, we will choose this type of source coding algorithm. Let me discuss few points related to types of the source coding algorithm in detail. Then we will go to the example of Shannon Fano coding in clear manner. Source coding techniques are mainly classified into two types. One is fixed length coding, another one is variable length coding. In fixed length coding, that output code word size is constant. What is the meaning of code word? Code word is in the sense unique identification of input symbol in terms of binary. Whatever the input symbol is there, that will be identified in terms of binary code word in the length of V or N. So N or V number of bits will be used to identify a particular symbol in terms of digital logic. And the mode of transmission, especially that information is completely going to transmit in terms of only those code words. Now in the fixed length coding, the code word size is completely constant for every input applied data. For example, we can take pulse code modulation, differential pulse code modulation or delta modulation. These techniques are also one type of source coding algorithm. Input side, we given only in terms of continuous data, continuous analog wave. At the output, we will get only discrete binary symbols, which are 1 and 0 in the size of only V. In pulse code modulation, the size of V is with respect to the number of quantization levels. In delta modulation, the size of V is constant with respect to only 1 bit per 1 sample. So we can take those techniques under one type of fixed length coding. But whereas in the variable length coding, that code word size is completely going to change with respect to its probability of occurrence. That means chance of occurrence. We have the principles from the information theory. If we are going to send any message to carry some information, there is a dependency with respect to its chance of occurrence. And we have one important relation from information theory is that if any message having high probability, its information content is very low. And similarly, if any message carries very low probability, then its information content is very high. So that means that information content of a particular message is completely inversely proportional to its chance of occurrence. Now, in a comparison between fixed length coding and variable length coding, we can able to achieve very good results in terms of efficiency, in terms of the number of bits conveying for a particular symbol. We will get only good results for only variable length coding. That's why many applications are using with respect to variable length coding. In this variable length coding, we have two main algorithms. One is Shannon Fano coding, another one is Huffman coding. So these techniques are important in their own application. Let me explain you one of the Shannon Fano coding with respect to one simple example. With that example, we can easily understand how that symbols will be encoded in terms of binary code words. Let us consider one example which contains a discrete memoryless source X with 5 symbols, and its respective probabilities are 0.2, 0.1, 0.4, 0.1, and 0.2. So these are the given 5 symbols respective probabilities. Let us assume its symbols are X1, X2, X3, X4, X5. We can able to assume. Many times the question may not consist of what type of symbol it is. And here, symbol consideration is not at all important. Only the probability consideration is very important in that. That's why we can able to assume any symbols where in terms of the representation like x1, x2, x3 or y1, y2, y3, that is up to user extent. Let us assume 5 symbols are there, x1, x2, x3, x4, x5, and its respective probabilities are in this way. Probability of x1 is 0.2, probability of x2 is 0.1, probability of x3 is 0.4, probability of x4 is 0.1, probability of x5 is 0.2. So different values we have. Now, how we can able to encode this particular one of the symbol into the binary code? Here, the output of this coding algorithm is completely binary output, and you can see that size of the binary code word from one symbol to another symbol is completely random in nature. There is no any fixed size. That's why we have taken one point. It is under variable length coding. Now, in order to start the procedure of the Shannon Fano coding with an example, first of all, we have to look into all the given symbol probabilities. In that, few probabilities are high and few probabilities are low. Here, in order to start this procedure, either we can able to take the first step with a decreasing order of the probability consideration or increasing order of the probability consideration. Let me go with the decreasing order of the probability consideration, which is very easy to understand with an example. Now, here out of the 5 given symbol, here which one is high probability? 0.4. So 0.4 is the highest probability, and 0.1 with the 2 symbols we have with the probability 0.1. So these 2 are under lowest probability. So first of all, take 2 columns with the symbol xi and its respective probability p of xi. Now here we have taken this example. In this, we can notice that highest probability is how much? 0.4. So let us take that 0.4 is nothing but a symbol x3. Then after that, we have another second level of probability is 0.2, but we have 2 cases, 2 same probabilities we have. Any one of the symbol we can able to take first. It is not a matter whether you are writing for this 0.2 symbol or this 0.2 symbol, not a problem. Any one symbol we can able to prefer. Let me go with x1. Now similar kind of x1, there is one more symbol with the same probability of 0.2, that is x5. So that I am considering a third position. Then after that, x2, which is nothing but a 0.1 probability. Then last symbol x4, which is nothing but a same 0.1 probability. Now out of 5 symbols, so x3 is having 0.4 probability, x1, x5 having 0.2 probability, and last x2, x4 having 0.1 probability. So here I have taken decreasing order of the probability, right? So you can take increasing order, not a problem, but only one method, one unique representation like a standard we have to follow. So in the comparison between the two, here considering discrete decreasing order of the probabilities is the very easiest procedure comparing with the increasing order of the probability. Okay, so this is the second, this is the first step of the Shannon Fano coding. Now immediately we have to take few more columns under encoding steps. Here, so in this encoding steps, let me go with the first step. It may take 2 to 3 to 4 or 5 couple of encoding steps it will take based on the number of symbols in the input side. Right now, in the first step of encoding, here we have to look into the probability column. Now we know very well that total probability of any source will be 1. That means if we accumulate all these probabilities of the symbol, it will give the value how much? 1 only. So from the value of 1, all the given symbols will be distributed with respect to some probability. Now here among all this probability, we have to take exactly 2 divisions, just like a 50% of the probability one side, another 50% of the probability another side. So suppose here I am taking the first symbol 0.4. So 40% of the probability is for first symbol, remaining 60% of the probability is at second side. That means I am going to take 2 partitions in these 2. So generally we have to take this partition with respect to 50% each partition. So 0.5 one partition, another 0.5 is another partition, just like a division of probability 1 into the two parts, two equal parts, 0.5, 0.5. Now here 0.4 is only I have, zero point 0.5 I cannot able to consider. Then immediately we can able to take another value which is nearest to 50% division. See, suppose if I accumulate 0.4 plus 0.2, how much it will become? 0.4 plus 0.2, 0.6. So 0.6 is one part and remaining 0.4 is at another part. So this is the only one possible, right? So why? Because here I cannot take 0.4 at one partition, remaining 0.6 at another partition. Why? Because I have chosen decreasing order of the probability that I have to follow for all the followed by encoding steps. So that's why here I am taking 0.4 and 0.2. First two symbol probabilities I am accumulating, then I am getting the probability value 0.6. So 0.6 I am taking as a first partition, remaining 0.2 plus 0.1 plus 0.1. So this is under another partition. So with respect to this, I am going to take one partition line. Suppose you are getting exactly 0.5, 0.5, you can take from that point, not a problem. Clear now? So, but the thing is, we have to consider two partitions of the probability exactly 50%, 50%. If the 50% is not allowable, then another nearest one we can able to take 55, 60, 65, which is least value. Based on that value, we can able to go. So, in my application, in this example, 0.4 plus 0.2, 0.6 is the nearest value for the 50% consideration. So 0.4, 0.2. So this is becoming one partition, and 0.2 plus 0.1 plus 0.1. This is becoming another partition. Clear? Now 0.4 plus 0.2. This is 0.6 now. Now consider this partition line. Above this partition line, how many symbols I have? Two symbols. Now here the one important rule we have to follow for Shannon Fano coding is in encoding steps. After partition, after taking this exact division of partition, how many symbols are there in the above partition? How many symbols are there in above partition? We have to encode those symbols with symbol 0. Once again, I am repeating. After taking this partition, how many symbols are there above this partition? Those symbols will be allocated with the symbol 0, and below the partition line will be allocated with the symbol 1. Now, as per that, above partition, I have the two symbols x3 and x1. So I am taking symbol 0, symbol 0. And below partition, how many symbols I have? Three symbols. So these three symbols I am taking encoding with 1, 1, 1. So that after encoding with the first step, I got two zeros in the first half and three ones in the second half. Now this is the end of first step. In the same fashion, it will be encoded, it will be carried forward for the next step also. Let us go to the second step. I'm taking one more partition, one more column, second encoding step. Now, in the second encoding step, that previous partition will be carried out. So we cannot change, we cannot deviate. So this will be maintained till the end of last encoding step. Now, now you can ignore this part. Now see, you have the two partitions now with respect to this one, above one level, below, above one part, below one part. Now look into the above one part. Now already here it is one partition, right? Now above one part, how many symbols are there? Two symbols. Now whatever the procedure we applied for the encoding one, same procedure we have to do here. Clear now? So this is the one partition already we have given. Now the same rule what we applied for encoding step 1, same we have to apply for the two partitions. Now here you can raise the doubt like why we have to apply two parts. That means here already partition is there. So partition is there in the sense the part is divided. Now look into the above partition. How many symbols I have? Two symbols, 0.4, 0.2. Here we don't have any criterion to take 0.5, 0.5. Why? Because here only part of the probability values are here above partition. That's why in order to divide into two equal categories of the probability, we don't have any other alternative. Simply we have to take one boundary line between the two. Simply we have to take one boundary line. Why? Because we don't have any other alternative, right? Only two symbols are there. If you have 3 or 4 symbols, then from that you have to take exactly 50%, 50%. I will explain you in the second half. Now, as per this, we have only two symbols. Then there is no any alternative. So directly we have to take one more partition line between these two. Now, as per the previous rule, above partition line should be encoded with which symbol? Symbol 0, and below partition will be encoded with symbol 1 here. Now, the same way, we have to consider the same procedure for the below part also. Now, in the below category, how many symbols we have? 3 symbols are there. Now, look into its probabilities. Now, divide it into the exactly half. Now, you will understand the case what it is here. Now, this is 0.2, here 0.1, 0.1. So, total probability is 0.4. In the second part, total probability is 0.4. So, in order to divide it into two equal parts, it is better to take 0.2 at one side, 0.1 plus 0.1 another side. So, it is better to take one partition line from here, right? So that's why here I'm taking one partition line from here. Now, as per the same procedure, above partition will be encoded with a symbol 0, below partition will be encoded with a symbol 1, symbol 1. Now, the second step is completed. Now, now, now next we will go into the third step. Now, like this we will go. Now the question will be arised that when we have to stop this coding. Clear? So here we have to follow one more important condition from this Shannon Fano coding is, in order to go into the step by step, in any one step, in any one step, if you are having only single symbol, either above the partition or below the partition, then you have to leave that symbol there only. Once again, I'm repeating. In order to encoding this Shannon Fano coding steps one by one, we are going to take that symbol like a carry forward, right? So the question arises that when we have to stop. Clear now? So that stopping position is nothing but a very simple. After considering this separation and after encoding step by step, in any encoding step, if you are having only single symbol, that may be 0 or 1, either above the partition or below the partition, that symbol you have to leave there only. No need to carry forward. Now let me explain you clearly with this example. Now here, in the third encoding step, here look into the second step. In second step, above the partition we have symbol 0, and below the partition we have symbol 1. Ignore about these symbols, right? Only consider the above first two symbol. So with respect to the first partition line, we have only one symbol at first point and only one symbol at second point. That's why we have to stop this encoding for these two symbols here only. No need to carry forward. Why? Because above partition we have only one symbol, below partition we have only one symbol. There is no any alternative step to consider division of exact half, right? There is no any possibility. So that's why we have to stop here only, right? So first two symbols are stopped here. Now coming into the third symbol. Now this third symbol is only one symbol at above or below the partition. That's why this one also we have to stop here. Now coming for the last two symbols. Here we have the two symbols, right? So here we can take one more division here. One more division we can take. 0.1 probability, 0.1, 50%, 50%. So we can take one more partition. Now as per the same procedure, above partition symbol 0, right? And below partition symbol 1. Now there is no any fourth step, right? Why? Because first three symbols stopped here, and if you are taking fourth encoding step, this last two symbols also will be stopped here only. Clear? So that means all the symbols are stopped at third encoding level. So this is the another stage of encoding in Shannon Fano. Now encoding steps are completed, right? All the bits are stopped, then encoding steps will be completed. Now after this, what we have to do? Immediately we have to consider its code word. Take one more column to take code word. Yeah. Now to take the code word from this encoding table, we have to look this encoding table from left to right. See my mouse point, right? Left to right. So in this way, we have to look into that left to right here. Now concentrate on the symbol 1 x3. First symbol x3 here. If I'm taking x3 from left to right, here I can say only the two symbols are there. 0, 0. Clear now? 0, 0. So this 0, 0 I will write first. Right? Now after that, second symbol x1. Now look into left to right direction in this table. I can see the symbols are 0, 1 here in this direction. So again, I will take 0, 1 here. Similarly, third symbol XY also having same bits 1, 0 here, left to right direction 1, 0. And similarly, for fourth symbol X2, here I have 3 bits here. By looking the table from left to right, 1, 1, 0. So 1, 1, 0. Here, and last symbol X4, same size of the length, 3 digits are there, left to right direction, 1, 1, 1, 1, 1, 1. Clear now? So with this, code word generation is completed. Now once again I'm repeating, please concentrate. In order to take this code word from this table, we have to look every symbol from left to right direction. So left to right direction, how many symbols you given? Those symbols in together, we have to take like a code word. So for first symbol X3, 0, 0. Second symbol X1, 0, 1. Third symbol XY, 0, 1, 1, 0, sorry. Fourth symbol X2, 1, 1, 0. Last symbol X4, 1, 1, 1 we have. Clear? Now, see, these are the unique code words that will be followed to represent these given symbols in terms of binary. Clear? So this is the another stage of Shannon-Fano coding. Now, the last stage of Shannon-Fano coding is we have to calculate how many bits in each code word. That is nothing but a n suffix I. Now see, in the first code word, how many bit digits we have? 2. In the second code word, again we have 2. In third code word, again we have 2. Fourth code word, we have 3. And fifth code word also, we have 3. Clear? So in this way, we will encode Shannon-Fano coding for any given symbol. Now, how we can say this procedure is valid? So for that validation checking, we have the few principles. In that, the first one, see, whatever the symbol having highest probability, it carries only less symbols. Apart from the complete symbols, if you see, the higher probability of the symbol carries only less number of bits. See, here in this table, high probability is 0.4. This is for first symbol X3. And if you can see the number of bits in this code word, here, 2. Number of bits in the code word is how much? 2. Clear? And similarly, for lower probability, that is 0.1, 0.1, 0.1, for the last two symbols. And if you can see, the number of bits in the code word is how much? 3 and 3. That means what we can conclude, if the probability is high, number of bits are very less. If the probability is low, number of bits is high. So this is nothing but a information content. So from the principle of information theory, same notation we have taken, right? If any message having high probability, that carries less information, and if any message having low probability, that carries high information. So here high information or low information content is nothing but a number of bits that we are following for every one symbol. Clear? So in this way, we can able to identify our procedure is correct. And similarly, there are few rules are there in the Shannon-Fano coding. What are those? The first rule is nothing but at the time of encoding of this all steps, see, in this encoding steps, if you can see clearly that first bit, first symbol will be stopped at first position, second symbol will be stopped at second position, third symbol will stop at third position, last symbol will stop at last position. In this way only we have to go. Once again I'm repeating, here very important tool in the Shannon-Fano coding is the first symbol should stop at first position. Last symbol should stop at last position. If it is not following immediately, here you can see the variation of the code word. Clear? For some higher probability, you may get higher number of bits. Lower probability, you may get lower number of bits. So that's why that will be taken like a very important condition in the Shannon-Fano coding, that stopping of the symbols should be with respect to probability way. High probability symbol should stop at first, low probability symbol should stop at last. And if you can see the number of code word bits, ni, it should be increasing way. How we have taken decreasing way of the probability, same fashion, here number of bits in the code word should be increasing way. Then only we can able to say our coding procedure is perfect. Clear now? So these are the few rules and conditions that we have to follow in the Shannon Fano coding. I hope this example and this lecture given you clear view of Shannon Fano coding. In the next lecture of mine, we'll see few more coding algorithm with a different example. I hope you like it. Thank you for watching. Thank you.